Yeah, good morning, everybody. I hope all of you in good condition. Okay, so we have learned about roots of equations, yeah, and you have some which is about finding the roots of equations using four methods. Yeah, four methods that we have learned before. Now, today, is there any problem with no? Okay, so I think it's yeah, it's not difficult, yeah, but we have to.
Ma'am, excuse me, ma'am. Your voice is uh, putus, ma'am.
Yes. Oh, okay. Wait for a while. Yeah. Can you hear my voice now?
Yes, ma'am. It's clear.
Okay. All right. All right. Thank you. Okay. So here, yeah, we will talk about. Yeah. Is there any problem for the assignment before we start on part 3?
Inshallah, no problem, ma'am.
Okay, no problem. Okay, that's good. Yeah. As long as you follow the procedure, so yeah, I think there will be no problem. And yeah, I think all of the method, including the open methods, was converging. Yeah, so converging and have a solution. So that is good. Yeah. Okay, so now we will continue on part 3, which is about the set of linear algebra equations. Perhaps you have learned about this before, in which if, for example, we have several equations to solve for several unknowns here. Yeah. So say we have n equations, which is the first function and the second and so on. Yeah. And if we talk about roots of equations, so that we find that the value of the function will be equals to 0. Now we don't talk about roots of equation anymore, but we are going to talk about solving a set of linear equation in which we have n equations to solve for n unknowns. Yeah. So for example, if we have here from f1 to fn, which are different functions, and each of those functions, yeah, contains variable x1 up to xn, and we have to find the value of x1 up to xn, which will satisfy all of these equations. Yeah, so this is called the set of linear algebra equations. And if we talk about linear, yeah, so if we talk about set of linear algebra, it means that the order of the equations that we solve are in power of 1. So this is linear equations. And this is what we are going to discuss, yeah, now. And also we can have a set of algebra equation in which the equations are not linear. So for example, equations of power 5, yeah, or 3, and so on. So this is called as a non-linear equations. But now we will focus on only on set of linear algebra equations. And why we are talking about set of linear algebra equations, because this system, yeah, arises in many applications, such as in partial differentiation the partial differential equations, in which we are going to talk about that later. Yeah, so that this becomes the basis. So that's why we are going to learn how to obtain the solution for this system. Yeah. Now, before we learned on the algorithm to solve, to solve for this problem. Now we will see. We will look on the review of matrices, and I think you have learned about this before. Yeah, you have learned about this in calculus. Yeah, when you learn about matrix. Okay, so we will do some review on that. Yeah, so say we have a matrix A, in which matrix A here will contain elements inside. So here, for example, we have M column and we have N rows. Yeah. So that the elements inside the matrix A here can be written as Aij, in which the first subscript here denotes the row and the second subscript is the column. So that say I have A21. So that means that this is the element that fill the second row in the first column of matrix A. Yeah. So this is how to locate or to denote the element inside the matrix A. Aside from the matrix, we also have vector. Yeah. So vector means only one row or one column. So we have a row vector here in which we can write down that the elements of the vector will be one row and n columns. Yeah, one row and n columns. While we also have the column vector in which we can write down the vector as here one column only and includes several rows. So we have C1 up to Cm here. And we have the term square matrix. Yeah, if the size or the number of row is equal to the number of column, so that means square. Yeah. So if we have the number of row is equals to the number of column, and say we are solving for n equations, yeah, to solve for n unknowns. So this means that the matrix which will be built by the system will be a square matrix. And also we have the term of main or principal diagonal. So this is the diagonal element that fills the matrix. So say we have here, so what is the main or principal diagonal? So it will be the diagonal element here. So this is called the main or principal diagonal. Yeah, main or principal diagonal. So this is the diagonal element. And we have the terms of symmetric matrix, yeah, symmetric matrix, if the value of the elements are symmetric in regards to the diagonal line. So say we have a symmetric matrix, it means that we have a matrix which is symmetric, so this is act as a mirror line, so that the value here will be equals to the value here and so on. So if we have the value here, so that will be similar as well. Yeah, so this is called symmetric matrix, and this one. Yeah, so that symmetric matrix will be for square matrix, yeah, in which it is symmetric in the diagonal in regards to the diagonal line. And we have the term of a diagonal matrix if the matrix contains all zero except the element in the diagonal. Yeah, so if we have the diagonal matrix, it means that all the value here will be zero except the diagonal element. And we have the term identity matrix if we have a diagonal matrix in which all the element is filled with one. Yeah, and this identity matrix is called one. Why this is called identity matrix? Yeah, so if we have a value of that, yeah, so this is the example of identity matrix. So why this is called identity? Anyone knows?
I would like to try to answer, ma'am.
Yes, Nicholas?
Can I answer it in Indonesia?
Yes.
Soalnya kalau misalnya suatu matriks dikalikan dengan matriks identitasnya itu hasilnya tuh ya matriks itu sendiri, nggak berubah.
Yes. Yeah, that is correct. Yeah. So why this is called identity matrix? Because when we multiply a matrix with this matrix, so that the result will be the matrix itself. Yeah. And this identity matrix is a diagonal matrix in which the elements all is zero. Sorry, one. Yeah. All the diagonal element is one. Okay. So we also have the term of upper triangular matrix. So upper triangular, when we talk about triangle, so this triangle will be divided into with the diagonal line here. Yeah. So if we talk about upper triangular matrix, so the square matrix A here is an upper triangular matrix if all the element of A I J is equal to 0 for I 1 up to n, j 1 up to n, and I is greater than j. So what does that mean? It means that all of the value here for the lower part here are 0. Yeah, so these are 0 elements. Yeah, and the elements that has values, yeah, the elements that have values are only on the upper triangular part of the matrix. And as the opposite, we also have the lower triangular matrix. Yeah, in which for the lower triangular matrix, it means that the elements only fill the lower part. Yeah, the lower part of the matrix, while the upper part of the matrix here are zeros. Okay, so that we have the term of inverse, yeah. So inverse is a matrix, yeah, in which if it's multiplied by matrix A, so the result will be identity matrix. So I think we have learned of finding the inverse of the matrix in calculus as well, yeah. So that the matrix which is multiplied by the invert, or on the other way around, if you have an inverse of the matrix, which is multiplied the matrix itself, so the result will be the identity matrix. And we also have the term, the transpose of a matrix if, say, here we have P, matrix P is the transpose of matrix A if Bij is equal to Aji, or shown as A transpose here. And I think we have learned about this before. So that transpose means that we changing, say we have an element in column, so that we will change it in rows, yeah? So that we will change this in rows. So the rows become the column and the column becomes the rows, yeah? So this is for the transpose of the matrix. So these are the special matrices, and these terms will be used throughout this part, yeah? So here we have symmetric matrix. This is the example. So we have symmetrics in regards to diagonal line here, yeah? And we have the diagonal matrix. This means that all of the value here are zeros except in the diagonal. So here the zero values are not written in the matrix, yeah, but this value are actually zeros. And we have identity matrix if we have the diagonal matrix in which all the elements are one, yeah. And we have upper triangular matrix. So this is the upper triangular matrix and lower triangular matrix. Yeah. So we have those terms already. So that now we will continue on matrix multiplication. Now we have learned about this before. Now this is just to remind you that if we have a multiplication of A, matrix A multiplied by matrix B, so the result will not be equal if we multiply matrix B with matrix A. And how to perform the matrix multiplication, now we will not discuss again because we have learned that before. Now we have the terms of augmented matrix. So what is meant by augmented matrix is that this is a way of putting two matrices together. While what is the meanings is actually this shows two different matrix or factor. Yeah. So here, for example, we write an augmented matrix A augmented with B so that we can write it side by side, yeah, side by side. But still, this is separate. So not getting into one matrix, but still we have two separate here, but just a way of putting it together, yeah, putting it together side by side. Okay, so this is called augmented. Yeah. And also we have the term of the determinant of a matrix, and you have learned about this before. So determinant is a single number, yeah, and we can write down the determinant as what is A, such as in the absolute sign here, yeah. So this is the determinant of a matrix. Okay, so those are the terms that we are going to use so that when we meet that terms, so you are not confused, yeah. So now we will go on the first chapter in part 3, which is about Gaussian elimination. So say we have a system of linear equation in which we have three equations to find for three unknowns. So the number of unknowns here are 3 or less. So this is quite easy. Yeah, it means that we will have a matrix in which we have 3 by 3. Yeah, the matrix size will be 3 by 3 to find for the unknowns x. Yeah, if the right hand side is known, for example. Yeah, so we have matrix A multiplied by x, that will be a factor B. Yeah, in which for this we already know the coefficient matrix A, and we already know the right hand side. Yeah. Now the problem is finding the unknowns. Yeah. So here is the unknowns. Okay. So how to solve that one? There are several ways that we have learned before. Yeah. First is the graphical method, and the second is the Cramer's rule, and the third is elimination. So method of elimination is basically eliminating some variable, and then we end up with one variable so that we can find the value of that, and then we can use it to find the other variable. So that these are the methods that we have learned before in calculus. Now we are going to apply numerical method for solving very large number of linear equations. So if we have small system, yeah, in which we have the unknown 3 or less, so it will be very easy to use one of these method here. But the question is, for example, what if we have 1,000 equations to solve for 1,000 unknowns, yeah? So how can we do, for example, one of the method here? So it will be quite difficult. So that here we will discuss about several methods in which this will be discussed in chapter 9 and chapter 10. Yeah. In which in chapter 9 we will talk about Gaussian eliminations and several modifications to that. And also we will talk about in chapter 10, which is about LU decompositions and matrix inversion. Yeah. In chapter 10. Okay, so we will look for the first method here, which is about the graphical method. Yeah, so this is the easiest one, in which, say, we have two equations to solve for two unknowns. Yeah, so we see here that we have two linear lines here. So this is the first line, and this is the second line. So that say we want to find for the solution, yeah, it means that we will find the value of x1 and x2, which will satisfy these two equations. So that how can we do it in graphical methods so that we reconstruct the equations so that we have the second variable as a function of the first variable. Yeah, or we can write it down as this one. So we arrange, we take x2 here, and x1 we move that to the right hand side, So that becomes negative A11 x1. And then we divide all of them with the coefficient of x2, which will be divided by A12 and A12 here. So that this means that we have x2 will be a function, a linear function of x1. Or we can say that x2 will be equals to the slope here of x1 plus the intercept. And again, for the second equations, we also reconstruct that one so that we have the similar linear line. Yeah, we have the linear line as well, so that we can draw it like this one. Say we have two equations. Yeah, so the first equation is 3x1 plus 2x2 will be equals to 18. So we can draw it here, x2, as a function of x1. And how to draw it? To plot it, we can just insert the value of x1 here. For example, we insert the value of 0, so that we have the value of x2 will be 9, and so on. We plot the points here so that we can draw the linear line. Again, for the second line, we do the same. So this is for the second equations. So that the intersections of these two lines will be the solution. Yeah. So that the value of x1 and x2 here will be the solution. Yeah. Will be the solution for this case. Yeah. So that in this case, we have x1 is 4 and x2 is 3. So this is for the graphical method. So it's very easy if we have small system. Say, for example, we have three. Yeah, so we have three equations to find three unknowns. So that means we will have a 3D coordinate system. So then we have to add in x3 direction, which is x, y, z. Yeah, so there will be 3 axes. So that the solution is the point where these these planes intersect. Yeah, so that if we think of n3 is already quite complex. Now, what if we have n greater than 3? Say we have 1,000 equations. So how to do the graphical solution? So this is not practical at all. So that what we can do is that now we can find the other method, yeah, which will be about the Cramer's rule and the method of elimination. Now, before we discuss into the other methods, we will look here from the graphical methods, yeah, that there are some systems, some problem, yeah, which, for example, here in A, we have two equations, for example. We have the first equations and we have the second equations, yeah. And then we want to find the solution. So in this case, because the lines that from the system, yeah, from the equations that constructed by the problem, we have two parallel lines like this one. So in this case, we never have a solution. Yeah. So say we have a system in which we have a matrix filled with minus half and 1 minus half and 1 as well here, multiplied by x. So that will be equals to 1.5. In this case, we never get a solution because physically there is no solution for this one. Yeah, so these two lines are parallel lines, so there will be no intersection. So it means that this will be no solution condition. Now we have another system in which we have two equations. Yeah, but we have two equations here in which the second equation is actually twice of the first equation. So this is actually the same equation, so that we will have two lines in which these two lines coincide coincide one another. Yeah, so that berhimpit, yeah, coincide one another. So that what happens here? So that we will have all of this line here will be the solution, because all of the points here, yeah, in the lines will satisfy both the first equations and the second equations. So in this case, we will have infinite solution. So that if we have infinite solution, this means that we don't have unique solution. Now, this is very important because what we want to find from a problem, when we want to solve a problem, we want to have a unique solution. It means we have only one solution. So that if we came across this sort of problem, so that means either the first one or the second one here, it means that we don't have a unique solution. Yeah. So in this case, there will be no solution for the system that we get. Now the third one here, we have an equations which is like this one. Yeah, so this is the first line. Yeah, this is the plot of the first equation, minus 2.3 over 5 x1 plus x2, that will be equals 1.1. And we have the second equations here, second line. This is minus half x1 plus x2, that will be equals to 1. So if we see here that these lines are different, yeah, different lines. But we see here that it's almost coincide. So that here we have a value which is not very clear here. Yeah, it might be here. Yeah, so that we have a unique solution, but it's rather difficult to get it. Yeah, and this is called as ill condition. So there is a unique solution. But the solution is not very easy to get. And what happened here if we have an ill conditions is that it's sensitive to the round of error. So for example, here, what is meant by sensitive to round of error? So for example, we have a change of value, yeah? For example, we have a change of value in X, for example, so that the Y value will be changing as well. Yeah, so we move a bit here to the left. Yeah, it can be, the result of X2 here can be very different. Yeah. So that this is sensitive to round of error and this is to be ill condition. And sometimes, yeah, for the actual cases, sometimes those cases fall into the ill condition system. Yeah, so in that case, it's a little bit different to get the solution. Okay, so if we see from the calculus or mathematically, we see that matrix A and B here are called as a singular. Yeah, so there will be no unique solution. And if we want to try to calculate the determinants, so that the determinants of this coefficient matrix are 0, and we cannot get the inverse of this matrix. There will be no inverse of the matrix A here. Now, if we look at the ill condition problem, so we can say that ill condition matrix is almost singular. So it has the unique solution, but it's not really easy to get it because it's extremely sensitive to the round of error. Okay, so that these are the problems that may arise from the problem of set of linear algebra. Yeah. Okay, so because we talk about determinants, so that now we will look at the Cramer's rule. So basically the Cramer rules is utilizing the determinant to find the solution. Yeah, so we can see here, say we have matrix A multiplied by a factor of unknown X that will be equals to the right-hand side factor B. So that, for example, we have 3 by 3 matrix here, so that we can write down the elements of the matrix A. So that we can find for the determinant. Yeah, so this is how to find for determinant. So that here we find the value. So usually this is positive, negative, positive. So that if we take this one, A11, yeah, I think you still remember A11. So that will be multiplied by A22 times A33 minus A32 times A23. Minus, next we take this one, so that will be A21 times A33 minus A31 times A23, and so on, plus the next one here. Yeah, so that we have A21 times A32 minus A31 times A22. Or sometimes we write it down like this one. Yeah, I think you still remember. Yeah, so that we do the calculation like that one. Yeah. Yeah. Okay, so this is to find the determinant, basically finding determinants. Once we have the determinant, so that now we can find the value of x1 here. Now you see here that how many calculation is needed here. Yeah, and it's rather complex and then finding X, and now we take B1, B2, and B3 here. Now we take A1, A2, to A2, A1 to A2, and so on. Yeah. So that we have to do repeated calculation of this one is not very easy. Now imagine if we have 4 by 4 matrix, yeah, to solve for 4 unknowns. So it will be not very efficient, yeah. So that for a large system, this Cramer's rule is not practical. So what we have learned in calculus is basically only for small system, because it needs to calculate the determinant. And we have seen here that calculating determinant is not very cheap. Yeah, it's costly. So it require many floating point operations. And also that, again, if we have a singular system, so D equals to 0. So again, back to the physical meaning that there will be no solution. Yeah, it means that the solution cannot be obtained. Okay, so that is about Cramer's rule. And because it's not very efficient, so that now we will look at the third method, which is about elimination. So this is the basic strategies to successfully, so repeat it, yeah, successively solve one of the equation of the set for one of the unknown. It means that we eliminating, yeah, the variable, so that we end up with only one variable, and then we can solve for that variable, and then we can return it to the previous equations, to the other equations, to find the other unknowns. Yeah. So that what is the advantage of this method is that it can be extended to larger system. Yeah. For example, if we have more than 3, for example, we have 4, 5, so that is quite the possibility to solve this is higher. Yeah, but also extremely tedious to solve by hand. Yes, it means that if you want to do it manually, it's not very easy. So that actually this method become the basis for the numerical method in which we will learn later, which is about Gaussian eliminations. So the basic concept is similar, yeah. So based on eliminating the variable, so we end up with only one variable, so that we can solve for that variable. Okay. So we see here the example of elimination. So say we have 2 by 2 equations here. We have the first equations and the second equations, and then we want to eliminate one of the variable. So say we want to eliminate x2, so that I will multiply the first and the second equations by a constant, so that we can eliminate x2 here. So then when we do addition, for example here, so that it will be 0. Yeah, so we will eliminate x2. So with this one, we have the value of x1. Yeah, we only have an equation in which it's only calculate one variable. So that we can calculate for the x1 value here, and then we can return it to the equation that we have here to find the value of x2. Yeah, so we insert here back in the equations, and then we have the value of x2. So this is the value of x2. And then once we have the value of x1 and x2, so that we can do checking. Yeah, we insert the value of x1 and x2 back into the second equation now. Yeah, and then we check whether the result will be similar to the right-hand side that we have here. Now, if we insert this into the calculation, so that now we have the value will be 5.500, and we have 4 here. So this is the difference due to round-off error. So this is the method of elimination, and I think you have applied this many times, yeah, during the calculations. Now, this become the basis for the Gaussian elimination. Okay, so now we will talk about Gaussian elimination, and this is called as a naive Gaussian elimination because we will work on the matrix as how it shows. Yeah, so that we will do the same thing that we have in elimination method, but now we will work on the matrix. So here we applying the elimination techniques or elimination method by developing a systematic scheme or algorithm. So basically what we do here is that we want to construct an algorithm so that the computer can work, yeah, using our algorithm. So the method consists of two stages. The first one is forward eliminations, so that we eliminate all the variable until we have only one variable left, so that we can solve for that one variable. And then once we have that variable, so that we do backward substitution, we insert it back to the previous equations that we have to find for the other unknowns. Yeah. Okay, so say we have here a system of n equations to find for n unknowns. So we want to find from x1 up to xn. So what we can do first, yeah, so we need to construct the matrix, yeah. So this one into a matrix vector multiplication. Yeah, so here we have A11, A12, and so on up to A1n. And again, the second row, A21, A22, up to A2n. And then this is a square matrix, so that we have AN1, AN2, up to ANN. And this is multiplied by a vector matrix of x1 up to xn. And the result will be the right-hand side. Yeah. So that will be P1, P2 up to Pn. Yeah. Okay, so that we have A, matrix A, coefficient matrix A multiplied by the vector of unknowns x, that will be the right-hand side vector of P. Now, to solve this one, we want to form the augmented matrix. So we have learned before, augmented matrix means putting it side by side. Means we put a matrix A with a vector B here. So that means we put together this one, the coefficient matrix, with the right-hand side. So that here, once we have constructed that one, so then we can do the forward elimination process. Yeah. So this is to reduce the system to an upper triangular system. So what we have here at the end of the forward elimination is that we will have an upper triangular matrix here. So all of the element here, yeah, on the lower part here will be 0. So what we can do is that first eliminate x1 from the second and the nth equation, so that if we have x1 up to xn, so that if we want to eliminate x1 from the second and the third equation, so that means we have to make 0 in the element here. So what we can do is that we multiply the first equation by a factor, in which the factor is a21 divided by a11, and subtract it from the second equation. So that becomes a new equation, the second equation. And then again, to make 0 here in the third row, so that we do the same. We multiply the first equation with a constant, which is a31 divided by a11, and then we subtract it from the third equation, and so on. So that if we do from rows to rows, from the second row up to n rows, so that it will create zeros for the first column below the first row. So this is what we have, yeah. So that by subtracting the first column, the first row with a constant to the second and the third, so that we have 0 here for the first column. And because this first row here is used as, we use that to subtract those elements. So this is called, the first here is called as the pivot element. Yeah. Okay, so once we have that finished up to n row, so that what we can do next is to make 0 for the lower triangular part here, so that we need to continue to the second column, and we try to make 0 below the pivot. So now if we go to the second column, so the pivot will be A22. So this is the pivot element. So that we want to make 0 below the pivot element. So we want to make 0 from the third up to n rows, and so on. So that we repeat the procedure up to the nth row, so that we have all 0 here. Now, once we have finished with this one, and then we continue to the third column, and we choose this one as a pivot element, and we want to make 0 below the pivot element here, and so on, up until we have all here. At the last row, we have only a and n here, that multiplied by xn, so that will be equal to bn. So once we have that value, so that we can easily solve for xn. So basically xn is only bn divided by nn. So once we have the value of xn, so that we can return to the previous equation. So once we have this value, so that we can backward substitution. So we go into n minus 1 equations to solve for xn minus 1 and so on up until x1. Last here is the last variable that we get from the backward substitution. Yeah. So this is called backward substitution because what we get is from the last row first and then we return to the first row. Okay, so this is how we perform the calculation, and this calculation can be generally written as this one. So xi, if we want to find xi up to the first equations, so the xi can be calculated by bi from I minus 1 minus sigma j equals I plus 1 up to n, ai j I minus 1 xj divided by ai I minus 1. So if you look at this mathematical subscript and superscript, it might be looks very complex, yeah? But actually the algorithm is very simple, yeah. Okay, so this is what we do. The first stage is forward elimination, so we try to make that original matrix A becomes upper triangular, so that keep remember in mind when we subtract, for example, the second row with the first row here. So it means that all the value here is also changing because when we subtract the equation, so that all the element here is also changing. So that's why when we subtract the second row from the first row, the other way around, yeah, we subtract the first row multiplied by a constant with the second row, so that we have this value will be changed, so that we give accent here. It means that it will be not similar to the initial value, and so on, yeah. So that once we have upper triangular matrix, so that we can find for x3, which is C3 double accent divided by A33. And then we get the value of x3 so that we can continue to the second equations, yeah, which is x2 is equals C2 accent minus A23 x3, in which we already get the value here of x3, so that we can calculate that, and all divided by the coefficient of x2. So here we have the value of x2. Once we have x3 and x2, so that we can insert to the first equations, so that we can find a11x1 plus a12x2 plus a13x3, that will be equal to c1. So that means if we have the value of x2 and x3, so that we can find x1. Okay, so basically this is the backwards substitution stage. Okay, so this is the Gaussian elimination method. So you see this is not difficult, yeah, and we can construct the flowchart, yeah, the algorithm to a coding, yeah, so that we can instruct the computer to do the elimination here and also the backward substitution stage. Okay, so this is what the code looks like, and this is written in Fortran. So we do looping, yeah, from k1 up to n minus 1, in which here we do looping from I, which is k plus 1 up to n. Yeah. So if we look at here I up to n minus 1, yeah. So this is looping for the row, and then sorry, for the column, yeah. So this is for the column. So this is, we look in the first column. Now for the first column, we want to make 0 for the second row. So that will be the row. Yeah, that will be the row. So this is looping throughout the column. Yeah. So throughout the column. And for each of the row, we have to make 0 for the rows below. Yeah. So starting from k plus 1, which is the row below, up to n. And then we find the factor first, which is the factor is aik divided by akk, which is akk is the pivot. So this one is the pivot. So that once we have the pivot value, so that now we want to loop, yeah, loop here, which is for the rows, row-wise, for the augmented matrix. So we have augmented matrix here, so that it will be row-wise. So we change the value of the element for all elements in the same row. Yeah. So once we finish with that row, yeah, row elements. So once we finish with that, so that we can continue to the second, the third row, the fourth row, and so on. Yeah. So this is forward elimination stage in which this will create upper triangular matrix. So once we have finished the looping up to the last n-1 column, yeah, so that now we can do backward substitution. Yeah, so that this is to find the first variable, which is xn, the last variable, and then we return to the upper one. Yeah, so this is for rows, upper rows. Yeah, and then for each of the rows we multiply this. Yeah, so we find the multiplication for yeah, so for the value, so that we can find xi will be bi minus sum over ai. Yeah, so this is we do the looping to the n-1 and so on up to x1. Okay, so this is the backward substitution. Okay, so that to make this clearer, now we will try on this example. Say we have 4 equations to solve for unknowns. Yeah. Okay, so that here we have 6. Yeah, so that we can write it down as a matrix here. So that we have 6 minus 2, 2 and 4, and the right hand side is 16. Yeah. And then we want to write down the second row, so that is taken from the second equation, so that will be 12. Yeah, minus 8, 6, and 10. Yeah. And the right hand side is 26. And the third row, again, the same one. Yeah, we write down 3 minus 13, 9, 3, and minus 19. And the last row is minus 6, 4, 1, minus 18, and minus 34. Now we want to make 0 for the first column first, for the first column, yeah. And we choose this element, the first element here as a pivot. Yeah. So how to make that 0? So to make that 0 is that we subtract the second row. So R2 is the second row. We subtract the second row with 2 times of the first row. Yeah, so that it means that we have 12. Yeah, here we have 12. So that will be 12 minus 2, in which 2 is actually, this 2 value is actually from A21 divided by the pivot A11. So the value itself, yeah, the value below the pivot divided by the pivot value. So that we have minus 2. So that here we have, because this one is 12 over 6, yeah, so that will be 2. So that R2 minus 2 times the first row, which is 6. So that will be 0. So that with this subtraction, so that means this will be 0. Now, when we do the subtraction of the equation, so that all of the coefficient here will be subtracted as well. So now we will continue calculating the second value here, so that we have minus 8 minus the same coefficient used, minus 2 times R1, which is minus 2. So that we have minus 8 plus 4, so that will be minus 4. So this value will be updated, becomes minus 4. Now the third element in the row, so we have 6 minus 2 times 2, so that will be 4. So that will be 6 minus 4 is 2. So this will be 2. And then we see here next we have 10. Yeah. So we have 10 minus 2 times 4. So that will be 8. So that 10 minus 8 is 2. Yeah. So that will be updated with 2. And then next, last here, the right hand side here is also changing, because we do the subtraction from this equation with this equation. Yeah. So that again here we have 26 minus 2 times 16. So that will be 32. So 26 minus 32 is minus 6. Yeah. So this will be updated into minus 6. So we see here that the second row now becomes 0, minus 4, 2, 2, and minus 6. So we will see here the result 0, minus 4, 2, 2, and minus 6. So we finish on the second row. Now we need to continue to the third row. Yeah. So now we want to make that 0. Now to make that 0, so that means we have to subtract 3 with a coefficient in which the coefficient will be the value itself divided by the pivot. So the value is 3 divided by 6, so that will be half. So that will be half of the value of the first row, 6. So that because this will be 0. Now we continue to the second element here in the row. So that we have minus 13 minus half times minus 2. So that because minus and minus is positive, so positive 1. So that will becomes minus 12. So that here we have minus 12. Next, the third element here, we have 9 minus half times 2. So that will be 1. So that is 8. So this will be updated with 8. Next, we have 3. So 3 minus half times 4. So that will be 2. So 3 minus 2 is 1. Again, this one we have minus 19. So minus 19 minus half of the value for the first row is 16. So that will be minus 8. Yeah, minus 8. So that will be minus 27. Yeah, so the result is minus 27. So here now becomes minus 27. So for the third row here we have 0, minus 12, 8, 1, and minus 27. So we see here 0, minus 12, 8, 1, and minus 27. Again, the same for the fourth row. Yeah, so to calculate this one, to make that 0, so that will be minus 6 minus the coefficient itself, minus 6 divided by the pivot. So that will be minus 1. Yeah, so that will be minus 1 or will be positive. Minus 1 is positive. And this is times the first row, so 6. So that will be 0. Now this one will be 4 plus the value for the first row. So that will be minus 2. So that will be 2. Yeah, that is 0, 2. And this one will be 1 plus 2. So that will be 3. And this one will be minus 18 plus 4. So that will be minus 14. And this one will be minus 34 plus 16. So that will be minus 18. Yeah, so we see the last row here will be 0, 2, 3, minus 14, and minus 18. So this is the result. Okay, so we finish eliminating the first column. Now, because we want to form the upper triangle, so that now means that now we have to make 0 for the second column here. Okay, so how to perform that one? Now we choose this one as a pivot. Yeah, so for the second column, we take the second row element here as a pivot. Now how to do the subtraction? Again, similar to before, so that we have now minus 12 minus the coefficient itself, minus 12, divided by the pivot element, which is minus 4. This is multiplied by minus 4. So that we have here is positive. Yeah. Okay, so that one will be positive. So that will be negative. Negative, negative will be positive. So positive 12, yeah, minus 12, positive 12, so that will be 0. Yeah, so that will be 3, yeah, 3, okay. So that now to calculate that one, that will be 8 minus 3 times. Now, because this is the pivot, now we don't subtract it with the first row, but now we subtract it with the second row. So that now we choose this element, 3 minus 2, times 2, yeah. So that will be 8 minus 6, so that will be 2. Yeah. So here we have 2 value, 0, yeah, and 2. Now last one, the fourth element here, so that we have 1 minus 3 times 2. So now will becomes 1 minus 6, so that will be minus 5. So here we have minus 5. So this is correct already. Last, we have on the right hand side, we have minus 27 minus 3 times minus 6. Minus 3 times minus 6. So that will be positive 18, yeah? And this is minus 27. So that will be minus 9. So here we have minus 9. So it's correct already. Now finish with that, we need to make 0 here. So to make 0 here, we choose here the diagonal element for the third column as a pivot. Yeah. So as a pivot, now what we do is that we subtract the fourth row with the third row, which is multiplied by a factor or a constant. So that here we have 4 minus 4 divided by 2, yeah, the element itself divided by the pivot element times the third row, which is 2. So that will be 0. Next, this one as well. So that will be minus 13 minus 2 times. Now, here will be subtracted with the third row. So minus 5. Yeah. So that we have plus 10. So that will be minus 3. So we see the result here is minus 3. Last, right-hand side, minus 21 minus 2 times here, the value is minus 9. So that will be plus 18. So that will be minus 3. So here is the result. So this means that we finish obtaining the upper triangular. So that will be the last of the forward elimination step. Now we continue to the second stage, which is doing the backward substitution. So remember again, so this is actually to find x1, x2, x3, and x4. So once we have that, so we can work on x4 first. So that means that minus 3 x4, that will be equals to minus 3. So that we can find the value of x4, which is 1. Once we have x4, so that we can continue to the second equations from the bottom. So that means the second equation is basically 2x3 minus 5x4. That will be equals to minus 9. So that if we want to find x3, so we can find it from minus 9 plus 5x4 divided by 2. So that if we have the value of x1 already, which is 1, so that will be minus 4 divided by 2. So that will be minus 9. So that will be minus 4.5. Wait. Do we have that correct? Yeah, so that is correct. Minus, so that is 1. So that minus 9 plus 5, so minus 4. So minus 4 divided by 2, yeah, minus 2. Okay, so that we have here, the result is 1 minus 2. And again, for x2, we can find it from here, from these equations. So it will be minus 4x2 plus 2 times x3 plus 2 times x4. So that will be equals to minus 6. So because we have the value of x3 and x4 already, so that we can find for x2. Once we have x2, so that we can find for the value of x1. So this is the result. Yeah. And this is called the naive Gauss elimination. So it is said to be Gaussian elimination. So that means we do the naive approach. So we just use the equation as how it is. Yeah. All right. Any question? Yeah. Is this understandable?
Yes, ma'am. Understandable, ma'am.
Okay. All right. Yeah, it's not difficult, but we have to be careful, yeah, because it's very prone to mistake during the calculations. Okay, so it's important that you really understand this method because our previous method will also using the same procedure, yeah. So if you do not understand any of this, you can ask, yeah, because later we will talk about other method in which the basis is actually the same, is based on Gaussian elimination. So it's really important that you understand this procedure. Okay. Now, if there is no question, so that I will continue. Okay, so now we will see here the example, another example of Gaussian elimination in which we use 6 significant figures, yeah. So that we have a total of 5 numbers, 5 digits after the decimal point here. So how to perform this one? So yeah, we can write it down as a matrix, as an augmented matrix, but in this example, it's written for the whole equations, yeah, for the whole equation. So it's basically similar, is that we want to find upper triangular matrix and that we want to make 0 below the pivot element here, yeah. So how to get the 0 element is to subtract the second row. So if we choose this one as a pivot element, so that now we subtract the second row with a factor which is multiplied by the first row. So that will be R2, the second row, minus subtracted with 0.1 over 3, which is the pivot element, times R1. So if we have that one, we subtract it so that the first element here for the second row will be 0. And next here we do the same. Yeah, so that will be 7 minus 0.1 times 0.1 over 3. Yeah, 0.1 over 3 multiplied by the first row, which is minus 0.1. So that here the result we have 7.003333x2. And again, we do the same for the third element in the row and also for the right hand side here, so that this value will be changing. Yeah. Okay, so finish working on the second row. Now we proceed to the third row. Yeah. The third row again, similar procedure, 0.3. So the third row minus the factor, which is 0.3 divided by 3 times the first row. So that we have this value, yeah, which is 0. Again, we do the same for the second. We subtract that with the first row, which is multiplied by the factor here, a constant factor. And then for the third row, again, we subtract with the first row with a constant factor. And also the right-hand side. So once we finish making 0 in the first column, so that we can continue to the second column, yeah. Now, the diagonal element here as a pivot, so the second row, yeah, second element, second row here. So this act as a pivot, so that we try to make this 0, so that we try to make that 0 by subtracting the third row with the first row, which is multiplied by a factor. So this will be minus 0.19 divided by 0.1 times 0.1. So this will be equal to 0. And we do the same. We subtract the third element here with the first row element, yeah, which is multiplied by this factor. And again for the right hand side. So now we have the upper triangular matrix already, yeah, so that now we can find x3 value. Again, once we have x3, we can calculate x2. Once we have x2, so that we can insert to the first equations to find x1. So that will be the backward substitution step, and this will be the solution. Okay, so if we see here that this is the solution that we get, yeah, including the round of error. Now this is the exact solution, so very close to the exact solution. Yeah. All right, so this will be the Gaussian elimination procedure, and we can see here that what error is actually included in here is only about round of error. So there will be no truncation error in this case, yeah. So all of the error here will be the round of error. So that if you want to calculate the operation needed, how many flops, yeah, how many flops are needed for this procedure, so that we see we have the inner loop, yeah, this is for forward elimination. We have the inner loop, and then we have the second loop, yeah. And also we have the outer loop. Yeah, so the outer loop, we have seen before, we have the looping for the column, and also for each for the column, and also for each of the column we have to loop for each row, and for each row we have the inner loop to subtract the element in the row with the pivot rows. Yeah. Okay, so that a total of, yeah, if we see here that this is in the order of n, and this is in the order of squared n, and this one is at the order of 3. Yeah, so that this is the forward elimination step. And for the backward substitutions, we have the inner loop, which is the calculation in the certain row, while the outer loop is when we search on for the when we do backward substitutions to another row. So that this will be in total, the largest one here is the order of 2. So that the total flops that is needed, we have the forward elimination stage and the backward substitution stage. So that will be roughly, yeah, about 1/3 of n to the power of 3, in which n to the power of 3 here is the number of equations. So say we have 100 equations, so that will be 100 equations to the power of 3. Yeah. So that will be 10, 100, so that 10 to the power of 6. So that will be 1 million divided by 3. Yeah. 1 million divided by 3. So this is the number of operation needed. Okay, so this is about Gaussian elimination. And yeah, regarding this method, there are some pitfalls using this method. First is division by 0. So say, for example, we have the first equation such as this one, in which the value has 0, x1, for example, like this. Now this becomes a problem because when we want to make 0 here, so that the pivot element is 0. So what happened here, if we want to subtract that one, so that we subtract the second row, R2, with A21 divided by A11 multiplied by R1. So that if we apply this, if we want to calculate this one, so we have the A11 value which is equals to 0. So the division with the pivot element is 0. So that if we have a division of 0, so that will becomes a problem. Yeah. So there will be an error in the calculation. So that will be runtime error. Yeah. So then the error, the calculation will just stop. Yeah. And do nothing. Yeah, because we have division with 0. Another problem is that dealing with round of error. Now, in the previous example, we have up to 6 significant digits. So that in that case, we have a calculation which is close to the real solution. But what if we use less significant digits? So that can be a problem as well. So the error will be quite large. And also if we have an ill-conditioned system, yeah, an ill-conditioned system. So such as, for example, this one, say we have a first system, which is x1 plus 2x2, that will be equals to 10. And then second equation is 1.1 x1 plus 2 x2, that will be 10 equals to 10.4. So this, when we solve the system, so that the value of x1 and x2 for the solution is 4 and 3. Well, say, for example, if during the calculations to obtain the coefficient matrix here, we have a slightly reduced value, very close to that, but slightly reduced value. Now, initially is 1.1. Now we insert 1.05. Now we see here that the result for this system now changing a lot. So initially 4 now becomes 8 for x1, and x2 initially 3 now becomes 1. So this is called an ill-conditioned system. It means that when we change a little bit of value there, yeah, in the coefficients, so that will result in large change in the solution. Yeah. Or another example, as we seen before, if we have two equation which is almost identical. Yeah. So we see here that it's very sensitive to small changes, and that the small changes caused by a round of error can also lead to very large difference of the solution. Yeah. So this is the pitfalls of Gaussian elimination. So some problems that may arise in using Gaussian elimination. And also the last one is about singular system. So if we have two equations that are identical, so there will be no solution. And this, I think this is a general, yeah, for general method. If we have singular system, so there will be no solution. So how to check for singularity? How to make sure, how to check if the system has a solution, so that we can find a determinant, yeah. So that we can check for the determinant of the singular system. Yeah. So here, when we doing Gaussian elimination, so here we say that after getting the forward elimination process and getting the upper triangular system, yeah. So when we finish that one, upper triangular system, so that the determinant for such a system is the product of all the diagonal elements. It means that if we multiply here the diagonal element for the upper triangular matrix, so that will be the determinant. Yeah, that will be the determinant. So that if the determinant is 0, it means that one of the element here is 0. So that means if we have constructed upper triangular matrix and it comes that one of the pivot element here is 0, yeah, one of the diagonal element here is 0, it means that the matrix is singular, yeah, or there will be no solution. Okay, now dealing with those problems, so there are some techniques to improve the solution. Yeah, the first is use more significant figures. Now this is dealing with round of error. So again, I will repeat this, that as try to include more, yeah, significant figures if we can, yeah, because this is dealing with round of error. The second is pivoting. Yeah, so pivoting means switching the rows. Yeah, so that if we see here that if a pivot element is 0, so that elimination step leads to division by 0. Now the same problem may arise when the pivot element is close to 0. Yeah, so that what is the main aim here is to avoid zero value as the pivot element. Yeah. So how can we avoid this one? We can do partial pivoting. It means that we're switching the rows so that the largest element is the pivot element. So this is the best practice. Yeah. So please try to choose the largest element as the pivot element. So we are going to switching the rows. Or also we can do complete pivoting. So aside from searching for switching only the rows, but we can also switching the columns, yeah, which is called complete pivoting. But this is not very common to be performed, yeah, for complete pivoting, because it's add complexity, yeah, because the order of the coefficient matrix X, yeah, so if we have A multiplied by X, so if we changing the column, it means that we also changing the order of the unknown factor X here. Yeah. So that's why complete pivoting is not very common to be performed, but partial pivoting here, most of the time we need it, yeah, to ensure that we have a good solution. And also the third one is about scaling. So scaling here can help if we have ill-conditioned system. So this is to minimize the round of error. Okay, so we will check here the example. First one, which is about significant figures. Yeah, how the significant figures, the number of significant figures, will affect our calculation. Say here we have 2 by 2 matrix, we have two equations to solve for two unknowns of x1 and x2 here. So that we want to create the upper triangular matrix, so that we choose this one as a pivot, and then we subtract the second row with the first row, which is multiplied by a factor. So then when we, for example, subtract with the first row, yeah, so that will be 1.0 divided by 0.0003 times 0.0003, so that will be 0. And again, we do the same for the second element, so that will be 1 minus 1 divided by 0.0003 multiplied by 3. So that the result will be minus 1,199. And also for the right hand side here, we do the same. So that will be 1 minus 1 divided by 0.0003 multiplied by 20001. Okay, so that will be this result. So that here we can do, because we already get the upper triangular, so that now we can calculate x2. So this will be, x2 will be minus 6,666 divided by minus 999.0. So this is the result for x2. And if we insert the value of x2 here and then we find x1, so x1 value will be 0. So we see here the difference, yeah. What we have here, using only 4 significant figures, now the exact solution here that we get for this problem, the exact solution is actually x2 is 2/3, which is pretty close to what we have here. But the value of x1 is actually 1/3, which is quite far away from the value that we have here. What we have in the calculation is 0, while the value should be 1/3 or 0.333 and so on. So that we see here that we have large error here by including only 4 significant figures. Okay, so what we can do here, that we can try with different, with more significant figures in the calculations, and we can see here that as we increase the number of significant figures, say we use 5, yeah, for example, we have the value is 0.3. And if we use 6 significant figures, now increasing again 0.33 and so on, yeah. So that means that if we have a value, yeah, if we can include more significant figures, so that will be resulted in more accurate result here, yeah. So we can see here that is getting closer. Well, if, for example, we use only 3 significant figures, so say I would just take 3 values, so that will be 1.00, like that one. So that we have the value which is very far away from the result, so it becomes negative, while the actual solution should be positive. Okay, so this is dealing with round of error. Now next is to avoid, is to do pivoting to avoid division with 0. So we will see here that we will do partial pivoting, yeah. So that in this case, yeah, we will find the largest coefficient in the column below the pivot element and then switching the rows, yeah, so that the largest element becomes the pivot element. Okay, so we will see here. We have the same example as before. Now still using 5 significant digits or 4 digits after the decimal point. So we see here that, yeah, what we have before is, this is the first equation and this is the second equation. Now we do pivoting. We search on for the largest element here. Yeah, we search on for the largest element and then we switch that, use that as a pivot element. So that means we're switching the first with the second. So that now here the second becomes the first equations and the first becomes the second. So that now this becomes the pivot element. So that now we can subtract the second row with the first row, which is multiplied by a factor. So that will be 0. And again, we do the same for the second and the third element in the rows. Now with this calculation, we end up with the value which is close to the actual solution. So previously we got this 0. Now doing pivoting, we have x1 now approaching to the actual solution. So this is very good. Less similar significant digit, but we do pivoting so that the result here, the error is greatly reduced. Yeah. Next improvement is doing scaling. Yeah. So for example, here we keep only 3 significant figures. Yeah. So that means 2 decimal point, 2 decimal number, 2 numbers after the decimal point. So say we have 2 equations like this one, yeah, in which you can see the magnitude of the coefficient here is very different. One is 2, the other is 1,000, hundreds of thousands. Yeah, so we see here that very large difference. Now here we do forward elimination so that we make 0 here. So that we can calculate the value of x2 is 1 and x1 is 0. Now the actual solution, the exact solution, is actually x1 is close to 1, while x2 is close to 1 as well, 0.99. So you can see here that the error is very large. Yeah, very large error. Now what we can do, because we have a value in which the magnitude is very different, so that we can use scaling. So what we can do here, that we can divide the first row here with 100,000. Yeah. After that, we are going to pivot it. Yeah. So after we do scaling, and then we search on for the largest element. So that will be the second row. So that we pivot. So that now the second row becomes the first. So once we have this, and then we can do forward elimination. Now the result, x2 is 1 and x1 is 1. So you can see here that the result now, the error becomes very small. Yeah. Now, why we need to do scaling? So actually scaling is not really affecting the calculation directly. But with scaling, we now know that we need to do pivot. Yeah. So actually, scaling was useful in determining whether pivoting was necessary. But the equation themselves did not require scaling to arrive at a correct solution. So say here we have an example in which we don't do scaling, we do not do scaling, but we just do pivoting, for example. So if we pivot, the first row now becomes the second row, and the second row now becomes the pivot. So without doing scaling, we end up with the same solution as well. Yeah. So that means that scaling do not affect the calculation, but scaling here can be performed so that it will guide us to choose for the correct pivot. Yeah. So if we look in here, yeah. So basically, what is the main approach that can be performed to reduce the error, yeah, to improve the solution of the Gaussian elimination? So first is about pivoting. So we can see here that pivoting has a very significant effect, yeah, significant effect on the calculation of the Gaussian elimination. After pivoting, so that we can, yeah, the next one is adding more significant digits and so on. Yeah, but the most important thing is to do pivoting. Yeah, scaling as well. Scaling do not have a direct effect on the calculation, but instead it will help us in determining which rows to be pivoted. Yeah. Okay. Okay. So these are some methods, yeah, to improve the Gaussian elimination calculation. Now, any questions before we discuss on the example?
Ma'am, excuse me, ma'am.
Yeah, Sultan.
I want to ask about selecting the biggest value for the pivot. It's for it's just for clarifying. It doesn't change any value, right, ma'am? So itu cuman menukar saja, kan? Jadi kayak nggak ada value yang berubah nilainya kan? Kayak misal jadi minus atau apa gitu kan nggak ada.
Betul. Jadi hanya mengubah urutan saja. Ya, jadi hanya mengubah urutan saja. Jadi artinya sebetulnya kalau kita perhatikan ya dari persamaan itu kan kita bisa memilih mana saja yang kita pilih untuk apa menyelesaikan X1 dan X2 begitu ya. Artinya kita bisa memilih misalkan oh saya mau menyelesaikan X2 dari persamaan pertama dulu atau saya menyelesaikan X2 dari persamaan kedua misalkan. Itu kan sebetulnya bebas saja. Nah, artinya di sini memang tidak ada perubahan ya, tidak ada perubahan nilai, hanya menukar saja. Jadi kalau kita punya semacam ini hanya menukar saja. So there's nothing change, yeah. So the system is exactly the same, yeah. But we just changing the order. Now it looks very simple, but this will affect the calculation. So how easy it is to be calculated to get the solution, it really depends on this. Yeah. So as a general rule, if you have a set of linear algebra, always choose the largest element to become the pivot. Yeah. Always choose the largest element to become the pivot. That will help in the calculation. Yeah. That will make that will reduce the round of error. Yeah.
Oh, okay, ma'am. Okay, thank you very much, ma'am.
Okay. Yeah. Any other question? Okay, so we will look at the example now. Say we have this sort of system. Now, this system already consists zero coefficient. So of course, if we have zero coefficient, we cannot use it as a pivot element. Yeah. So this will be written in A augmented with B, in which here we write down as the original matrix. So we have 0, 2, 0, 1, and then 2, 2, yeah, 3, 2, minus 2, yeah. And then next, the third row is 4, minus 3, 0, 1, and on the right-hand side, we have minus 7, and 6, 1, minus 6, minus 5, and 6. Now, how to solve this one? This is impossible to be used as a pivot. Yeah, so that this cannot be used. So that we have to search on the value below. Yeah. So that will be 6 is the largest. So then we switch on. Yeah. We switch the rows. So R1, the first row becomes the first row and so on. Yeah. So fourth row becomes the first row. So when we change the position of the row, so all of this row here will be switched. Yeah, all of the element in the row, because this means switching the equation so that all of the element here should follow. Okay, so we're switching that so that now we have the first row now becomes 6, 1, minus 6, minus 5, and 6. So this now becomes the pivot. And then once you have this value, now we have to make 0 for the rows below in the first column. Okay, so that to make that 0, now we have R2. Yeah, so that we have R2 minus 2 divided by 6, yeah, 2 divided by the pivot element times the first row coefficient. So that will be 0. And again, this value as well. Now, 2 minus 0 0.3 times 1, so that will be minus 0.667. 3 minus 0 0.33 times minus 6, so that will be 5. And 2 minus 0 0.33 times minus 5, so that will be this value. Next, we have minus 2 minus 0 0.333, R1, which is 6, so that will be minus 4. Again, we do the same for the third row, 4 minus 4 over 6 times 6, so that will be 0, minus 3 minus 4 over 6 times 1, so that will be this value, and so on. Okay, so we finish zeroing the first column, and for the last row here, it's still 0. Yeah, it's still 0. Okay, wait for a while. Okay. Yeah. Once we finish with the first column, once we finish with the first column, so that now we will continue to the second column. Yeah. Now, when we want to set the pivot element, now we do searching again, finding the largest value. Yeah. So here, when we want to decide which one is the pivot, we don't use this value directly, but we search on for the largest value. And what is the largest value here? And the largest value is taken to be this one. So here we looked at the value as negative, but when we look at the magnitude, yeah, when we look at the magnitude, or we say in the absolute value, so the absolute value of this is larger than the others. Yeah. So that's why this value is taken, although it's negative, but this is the magnitude is the largest, so that this is taken, yeah, as a pivot, so that we're switching the second row with the third row. Yeah. So that we're switching the third row with the second row, so that now we have this one as a pivot element. Yeah, sorry for that. I've been disconnected again. Yeah, you still here?
Still here.
Yeah.
All right. Yeah. Okay. Okay. Sorry for that. Now we will return to hear about Gaussian elimination, in which we now have zero. Yeah, zero below the second pivot. Yeah, the second pivot. Now, when we finish that, and then we continue to the third column, yeah, continue to the third column, and then we search on for the maximum value again, yeah. So we search on for the maximum value, so that here we have the value is 6.8 and 2.1. So the largest value will be 6.8. So then we don't not do anything, yeah. You just don't do anything. So we keep that as what it is, so that now we try to make zero here. So once we have that value, so that now we can calculate x4, yeah. So that we have x1 up to x4. Okay, so that because we have the value of x4, so that we can return to x3, x2, and x1. Yeah, so that will be the backward substitution stage. So this will be the result. Okay, so this is the example of Gaussian elimination with pivoting. Yeah, so we can uh, perform pivoting so that the result will be closer to the exact solution. Okay, so I think that will be all for today. Is there any questions before I close the class?
Excuse me, ma'am.
Yes.
I want to ask about the changing of the row. Is
Yes.
there the rule is just if the value is bigger and then find the one with a lot of zero numbers, ma'am.
Fine. Can you repeat? Fine. The one with lots of
Lots of zero number on its row and the biggest value, ma'am.
Yeah. So that, yeah. For example, this one. Yeah. For the pivot. Yeah. For example, here. We try to find for the largest value as the pivot element, so that, for example, here we have zero in the pivot, yeah, so that this is required to be replaced, yeah, by another value because this is zero. But for example, we have the value of the first row is 2, so that we can also change the value with the pivot element, in which the pivot element will be the largest value. So we search on for the value for all the value in that column. Yeah, so we search on for all of the value in that column and find the largest and use that as a pivot. Yeah. Is that answering your question? I'm not really sure the question. Yeah.
I mean, if the row with consists of zero number is, for example, third row.
The third
Can
row
we,
here.
yeah, can we change it with the first row?
Oh,
I
yeah.
mean, it's like randomly.
Yeah. Yeah,
Okay.
that's fine. Yeah, that's fine. So even though, for example, yeah, the elements in that row consist of zero, that will be fine. Yeah, as long as the pivot element. So when we do switching, we only care about the pivot element. So we don't care about the other elements that following in that row, but we only focus on the pivot element. So say, for example, here we have 6 and 6 consists of 0 here, for example. So it doesn't matter. We can just use it because what we care about is only the pivot element. Yeah, only the pivot element. While the other element in the same row, it doesn't matter.
Okay, ma'am. So it's just to make sure that the pivot is not zero, and the other thing is the higher row is the higher value, ma'am.
Yes, yes. So the highest value that will be chosen as the pivot element. Yeah. And
Okay,
when we
okay.
do pivot, when we do pivot, we don't care about the order, So for example, we have here the order of the second and the third row is not in the correct order, for example. It's not like doing a sorting from the largest to the lowest now, but we only searching for the pivot element. We try to search on for the largest value, only that one. So we don't care about the others, but only finding the largest pivot element. Yeah. Okay, so that will be the answer to your question. William, any other questions?
For me, it's clear, ma'am. Thank you.
Okay, yeah. Thank you, William. What about the others?
Maybe not yet, ma'am. Maybe we need to read by ourselves, and then for the next week, if I have a question, I will ask you.
Yeah. Okay. Yeah. Yeah. Perhaps this needs practice as well. Yeah. So you can try on reading on this. Yeah. Did I uploaded the slide already? Not yet. Yeah. Okay.
Not yet, ma'am.
Okay. So inshallah, I will upload it. And in this chapter, aside from Gaussian elimination, we also have the Gauss-Jordan method, in which the Gauss-Jordan method is very similar to Gaussian elimination, but instead of doing zero, making zero only for the rows after, we also subtracted at the rows before. Yeah, so the upper rows and also the lower rows. Yeah, so this is the difference with Gaussian elimination. So the basic procedure, the basic steps to make zeros are similar to Gaussian elimination. So we see here that the other method that we will talk next week is based on Gaussian elimination. So please make sure that you understand the process here, so that we can discuss again next week for the other methods. Yeah, and next week we also discuss about LU decomposition, in which is also depends. It's also similar to Gaussian eliminations. Yeah, so the basis is the same. Okay. Okay, so if there is no questions, so I will close this class. Yeah, I will upload this in classroom, inshallah, and I'll see you next week, inshallah. Wassalamualaikum.